Okay. So obviously if we want to study Portland cement hydration, we want to first look into the process, like stages of the hydration, right. Many of you must have seen this, but anyway we will discuss it here. So this is the typical rate of hydration plot for Portland cement. So what do you see? You see there are 1, 2, 3, 4 different stages, right, you see. So 1, or here we is initial period, basically A. It is called heat of dissolution. So you have this cement and you are dissolving it in water. So basically it is nothing but heat of wetting and maybe some formation of products. Notice you have very high rate of heat, right. Does not mean that the amount of heat is also high, it is a rate. Any powder, for an example, even if it is non-reactive, you will have this heat of wetting. But in this case you have heat of wetting and some reaction, some dissolution, some formation of calcium silicate hydrate, for an example. So you have a rapid release, significant heat production rate, at least rate of heat hydration. Then what happens? It slows down, right. Then you come to this part 2. 2 is nothing but induction period. Okay. Now you see that the reaction has slowed down, does not mean that it has stopped, still you have a positive rate of heat of hydration. Can anyone tell what is the importance of this induction time, induction period? So it is valuable to us because it gives us some time. Yes. So it is also called dormant period. Okay. Why is it happening? What is the cause for this? Right, I mean those reactions will take place, but primarily what have simply you have a cement particle, it is reacting to something is forming on its surface. So imagine you have, so you have these cement particles. Now after some time you form something on the surface, right, that acts as a barrier, right. You have water, then it acts as a barrier for some time, right, but after some time this barrier breaks down, right, but it gives you some time to finish your concrete, for an example, or maybe transport it. So it is very important. So induction period, right. Then what happens? This is then the reaction accelerates. It is called accelerating period, very important, right. So lot of hydration products form during this period, right, and the peak you see is achieved around 12 to 14 hours, right. Then you see a slowdown. Now this is a deceleration. Why? Because you have formed so many products. Now imagine you have so many products, like you start with this, now you are making it difficult, right. Now it is a diffusion control, right. Yeah, if you want to make this remaining cement particle react, you have to cross this barrier, right. So it becomes diffusion control. So that is why you see this decelerating period, right. So this is again the rate. Pay your attention, does not mean that you have a positive rate, your total heat is increasing. So this, if we have to plot, for an example, now cumulative heat, right, the plot will be something like this. So this is total heat. Clear? So the total heat plot, you can see after this main peak, the slope changes, right. So, you have this acceleration period, then your slope is changing, right, but still you are seeing in this increase, right, it will go on. So, that was this decelerating period was D here, right. One more interesting observation here is you see something in this decelerating period, right. Here it is shown as E for an example, sulfate depletion peak. So, you use some gypsum in your cement, right. Why is gypsum used? Yes, right. So, to prevent flash set. But what happens when the gypsum gets consumed fully, you form monosulfate, right. Your eternite converts to monosulfate. So, this tells you about this sulfate depletion, tells you that whatever gypsum you have added is finally consumed, it is being consumed, right. So, it is very important because lot of times this optimization of sulfate is done through strength test, right. You optimize the strength, you add 1% gypsum, 2% gypsum, 3%, 4%, 5% and see which one is giving you the maximum strength. But calorimetry can also tell you how much gypsum should be added, you do not have to do destructive tests. So, again this calorimetry is a non-destructive technique. See the power of this measurement, tells you about lot of things, the rate, which are the critical stages, right, because it is very important to know. Suppose you want to extend this dormant period, suppose you decide that you have to transport your concrete to 30 kilometer away, which needs at least 1 hour for an example, maybe including traffic if it is 1.5 hours. So, you want to use some admixtures to delay this setting or prolong this dormant period. So, you can, what you can do, you can study, you can carry out these experiments and see what happens when you have these additives, right. So, we will come back to it, but I am trying to draw your attention that you can get lot of information. Clear? So, this is the typical Portland cement hydration. Our focus will be to study this. How can we use isothermal calorimetry or adiabatic calorimetry to understand it better? Continuing this Portland cement hydration, now suppose you have measured the heat evolved, right. So, here what you see on the y axis you have a mean heat evolved at different days, right, 3 days, 7 days, 28 days, 90 days, 1 year, 6.5 year, 13 years, and you have compared different types of cements. So, here ASTM type 1, type 2, type 3, type 4 cements are there. All of you must be familiar with this ASTM classification, right. So, you see that the type 3 cement, right. So, you have the highest heat, right, at all ages. Now, it is getting it's very similar to type 1 at later age, but at least at early age. Type 1, type 2, type 2 anyway has more, type 2 is low heat cement, moderate sulfate resistance. So, it has a little bit more C2S, less C3A. So, you see that this is the trend. Type 4 is low heat cement, right. So, it has more C2S, right. So, the heat is also, because the reaction is slow, right, because you have more C2S in the system, right. So, heat evolved is directly related to the amounts of clinker phases that have reacted. What you see here, you see the difference, right. That difference is because you have different phases. The phase composition of cements are different. Type 1 cement has maybe less C2S compared to type 4. Type 4 has more C2S, right. And the heat evolved will depend on the amount of each phase, how much C3S you have, how much C2S you have, because reaction is different, right. The reaction, each chemical reaction is different. If it is different, then the heat associated heat release is also different. So it depends on many factors such as particle size distribution. You all know that if you make your cement finer, you make it react more, you have more higher heat which is evolved. Water cement ratio, temperature and relative humidity of curing, these all will affect your heat, right. So how can we calculate heat of hydration? Next question, right. We know that okay, this is our hydration curve. How can we calculate? This is a simple calculation you can do. The total heat of hydration, right, can be written as summation of the contribution of individual phases. So through Bogue formulation you can find out how much C3S, C2S, C3A, C4AF you have in your cement, right. And now in this table you see that the value of coefficients is given, right. So for an example, if you want to calculate the heat of hydration at 3 day, what you do? You take the coefficient as 243 for C3S, right. If you know the C3S, suppose you have 55%, then if you know how much C3S you have, C2S, C3A, C4, so you know this. Now you just use the coefficients to calculate the total heat of hydration. Is it clear? Obviously these coefficient will not be same, right. So you see the coefficient changing, 7 day different, 28 day, 90 day, 1 year. In this case, I mean in this study they basically looked up to 13 years, right. So basically this simple relationship can be used to calculate the heat of hydration, right. It is nothing but the contribution from individual phases, right. Also you see here enthalpy of the complete hydration, that is very important, right. So like for an example C3S, if there is a pure C3S phase, that will release roughly around 517 kilojoule per kg. So that is a number for pure C3S, right. And similarly obviously C2S is slow in reacting, so you have 262 around kilojoule per kg. That means 1 kg of C2S, pure C2S will give you 262 kilojoule of heat, right. These are pure phases. So you use these to finally calculate. Now your Portland cement is nothing but a mixture of C3S, C2S, C3A, C4AF. Now you know the values for the pure phases, right, and you know how much C3S, how much C2S, how much C3A you have, right. You can calculate the total heat of hydration. And also see here for C3A, so this value 1144 is for the reaction with gypsum to give monosulfate, and 1672 is for the reaction with gypsum to give eternite, right. You have these reactions, different reactions. We are not going in detail, but in cement chemistry or any other class you must have learned the reactions, right. C3S when reacts with water gives you CSH, calcium silicate hydrate. Same thing C2S. C3A reacts with calcium sulfate or gypsum to give you AFT or eternite, right. Then AFT converts to AFM, monosulfate, right. Yeah. So these are the, it is good to know these enthalpy like for pure phases, because then if you know how much of it is, you will be able to calculate. Is it clear? Simply you are basically breaking down, right, your system. You are assuming that your cement is made of 4 phases. and if you know the amount of these phases and you know what is the enthalpy of the complete reaction, complete hydration of pure phases, you will be able to calculate total heat of hydration. Okay. Moving on. Now we know about the Portland cement hydration, right? And what are the phases which are of importance. Now we will focus on measuring, like how do we measure. So we will focus on primarily 3 types of calorimeters. Okay. Isothermal, as you can guess, isothermal calorimeter is used when you are interested in measuring heat at constant temperature, right. So in isothermal you maintain the temperature, constant temperature is maintained between the sample and surrounding. So the idea is, how do you do it? You have a, suppose cement hydration going on, and you know that the cement hydration will release some heat, and that heat you can remove to maintain the temperature. Obviously when the cement hydrates, the temperature will increase because there is a heat, right. If you can remove that heat, then you will be able to maintain. Now you are measuring that heat, the heat you are removing from the system, you are measuring it. So that way you are monitoring this process. Adiabatic, right. In adiabatic, what do we do? No heat loss should occur between the sample and surrounding, right. That is the ideal case, but usually the heat loss is small and almost constant. We will go over these techniques, but right now just to understand, these are semi-adiabatic is similar to adiabatic, but only difference is heat loss is not constant, increases with the rise in the temperature. Okay. So in adiabatic your heat loss is small and almost constant. In semi-adiabatic, heat loss is not constant, increases with the rise in temperature. Coming back to isothermal calorimeter. Okay. So we are maintaining the temperature, right. We want to maintain the temperature and then measure the heat, right. So what you have, heat flow or heat production rate is measured, clear. How do you do it? You have a reference sample also. So you have a sample, your sample, and you have a reference sample. Okay. We will come back to it. So reference sample without any heat production is also present. We will pick a sample which does not release any heat, and we are measuring the difference basically, right. So the output is the difference between the sample signal and the reference signal. This is all done to reduce the noise. Important point to keep in mind is the heat capacity of the reference sample should be same as that of sample. That is very important. Heat capacity of the reference should be same as that of your sample, but it should not release any heat. So for an example, you can take quartz or water for an example as a reference, right. Also isothermal calorimeter can be used for the paste mortars. So because the amount is limited, you can use typically 1 to 100 gram of sample, right. So small, you are not talking about kgs. So that is the also limitation of this technique. You can only use it for paste and mortar, right, and the amount is up to 100 gram. So you finally get this power, thermal power, right, changing with T. Thermal power tells you about the heat production rate, right. So this is a typical signal you get. We will convert it later, come back to it, but idea is you have a reference and sample, you are measuring the difference between reference and sample. Basically how are you doing is, the whatever heat is generated, right, whatever heat is generated, that is sent to the heat sink, right, heat sink. Then you are measuring the voltage, you are relating this change in that heat will cause some temperature difference, right. You have a flow sensor, heat flow sensor, that heat will cause temperature difference, that temperature difference will lead to the voltage, right. So you are measuring the voltage, And now think about, you have this sensor where you have voltage, you are also measuring the current, because right. So, once you know the current and voltage, you can calculate the power, or you can do it through current and resistance also, you know that. So, thermal mass of the reference sample should always be similar to the thermal mass of target, very important. Okay. So, I will show you how do we do it. Suppose you want to make a paste, right. You decide to add cement and water, right. That is how you make paste, right. And the heat capacity of cement is, in this table you can see 0.75 joule per gram per Kelvin, right, and water is 4.18, right. Suppose you decide that you are using 3 gram of cement and 1.5 gram of water, right. So, you can calculate the thermal mass of this system, cement and water. How will you do? 3 times 0.75 plus 1.5 times 4.18, clear? That is the thermal mass you are talking about. See, obviously this will change, right, if you want to try different water cement ratio, other things, if you want to add sand, but you can calculate what is the thermal mass, approximate thermal mass. So, in this case it comes out around 8.52 joule per Kelvin. Now, you want to keep this same. So, you want to calculate how much reference you have to use, right. So, suppose you decide to use water. So, what you do? You then, suppose R, I am saying reference rate. So, you know this is the thermal mass you have to get, and you know the capacity, right, it will give you 2.04. Simple calculation to show you that how do you balance, because now you are sure that your reference and sample have similar thermal mass, right. Basically heat capacities are similar, same. Now, you are measuring the difference, whatever is happening because of the reaction, you are measuring that, the difference, because right, the water is not going to release any heat. You can use quartz also, a lot of times commonly used reference is quartz, you can see here, right. So, the thermal mass of a given material is calculated by multiplying the mass of its specific heat capacities, clear? Okay, now you know about the isothermal calorimeter, it is simple, right. Now, we will come back to semi-adiabatic calorimeter. Semi-adiabatic, what we said about semi-adiabatic, that you want to have the constant heat loss, it will be small but constant. Ideally, you want to have a 0, right. So, simply your sample is insulated and the temperature increase is measured. So, imagine you have this sample, right, is insulated, right, because you want to prevent this heat loss, and you have embedded a sensor where you can measure the temperature T, right. Now, the question is how do you do it? So, you measure the temperature, but the corrections must be applied for the heat losses. You know that even though we have tried to make it completely insulated, but there will be heat losses, right. So, those correction you will have to apply and you measure the temperature. So, the typical output is this temperature versus time, right. But the advantage of this technique is that you can use the large samples up to, you can use mortar, concrete, right, up to 10 kg, right. But what is disadvantage? Anyway, we will come back to it. See what happens, you have made this very insulated. Now what happens, due to the reaction you will be heat release. That heat release will increase the temperature, and that increase in temperature will influence your cement hydration. You understand? In the isothermal case, we are trying to maintain the temperature. Whatever heat is being released, we are removing it and measuring that heat. In this case, we are measuring the temperature. This is the insulated system. So, heat will rise, that there will be temperature rise, that will affect your cement hydration. although you started at 20 degrees Celsius, but then as long as it, I mean as soon as it goes to 30, 40, 50 degrees Celsius, it will start affecting your cement hydration, right. So, see the both advantages and disadvantages, but the advantage is you can look into the concrete, close to reality, right. If you are using concrete in any building structure, you want to study how the concrete performs, like what is the interaction between cement and aggregates, other things. This is the final one, adiabatic calorimeter, similar to what we seen. In this case also we want to reduce the heat loss, but how we are doing, we are not insulating it completely, we are temperature of the sample surroundings is maintained at the same level. So, how we are doing it, we are saying okay, your sample due to the hydration will rise, right, the temperature will rise, but we are also rising the temperature around of surrounding, so that there is no heat loss, you understand. So, the sample surrounding is maintained at the same level, okay, as that of sample to prevent this heat loss. So, for that you may have to provide some additional heat, obviously, right. Your suppose cement is hydrating, your temperature is going up to 40, 50 degrees Celsius, then you have to raise the temperature. So, here is the schematic of this for an example, right. So, you see your sample, right, and you are measuring the temperature, right, and what you have this thermal unit conditioning, right, this your thermal jacket basically surrounding it, that is how you are maintaining the temperature, right, and obviously you want to insulate also the sample so that there is no loss, right, but the idea is you are maintaining the temperature of sample and surrounding. It is also commonly used for mortar and concrete, okay. Okay, so this is the adiabatic calorimeter we have at IIT Madras, okay. Now you know the principle of adiabatic calorimeter. You can see, suppose this is the big water tank, right, inside it we have this sample holder, right, it is the top view. Sample holder looks like this, right. So, you have put your concrete in this sample holder, right, and it is in the water bath, right. So, here you see yeah, so it is in the water bath. So, basically you are sensing the temperature of your sample, and also then you have a sensor in your water bath, and as you want to make sure that there is not much difference between the sample temperature and surrounding sample temperature. You have program controller, right, controller does that, it minimizes the temperature difference between the sample and finally, this is the last slide. We will start from here in the next lecture, but I just want to show you temperature, right. Here I am plotting temperature, we are seeing temperature versus time for 3 different types of calorimeters: isothermal, semi-adiabatic, adiabatic. Isothermal, no brainer, why it is same? Because we have made it same, right. So, you see constant temperature. Semi-adiabatic, you see increase in temperature. Why? Because you have this insulated system, right, insulated system. So, there is no heat loss. You have adiabatic. So, you see the difference. In adiabatic you have your delta H is very small, delta is very small even at high temperature. So, what happens with the semi-adiabatic, as you rise the temperature, even if you go like 70 degrees Celsius, your losses will also be higher, right. So, that is why you do not see, the question is why the adiabatic calorimeter gives you higher temperature than semi-adiabatic, okay. So, we will start from this slide in the next lecture.